Welcome back, everybody. Hey, I thought I would make a bonus video because I was just talking about switched versus hub-based topologies, or shared media versus switched media, or broadcast media versus broadcast addressing. And there was something in the video that, I don't know if you caught it, but I thought I would talk a little bit more about it, and that is the cabling. So let's take another look at that switched topology that I had up there. Alright, if we take a look at this topology, we can see that our PCs are connected to the switches, and we've got what looks to be a solid connection. And here I use these dashed lines. Now I could have gotten away without that. So over the course of the video, that's not the one I want. Delete that one. We'll just pick the same one. So I could have gotten away with this. So if I'd use my connection, I could take this guy here and connect them together. But we see that we've got, it starts off red, but we're going to eventually transition to green. Now we'll let that happen while we're talking here. But what is the difference between these? Well, if I mouse over it, we can see that, whoops, see there it says copper straight through, or you can see that on the bottom here, and one says copper crossover. So I'll just make that note here. So this is straight through. Oh, spelling counts. Straight through. And this dashed one is what we call a crossover. And there are a couple of times that we use straight throughs, and there's a couple of times we use crossovers. Now, traditionally, I will say that. So there's a couple of cases where we use straight through. We can use straight through when we connect PCs to network devices, when we connect routers to network devices. A lot of times, though, when we connected devices that were the same type, a hub and a hub, or a switch and a hub, a switch or two switches, two routers, two PCs together, we use crossovers. And that's because we were trying to get the transmit lines to the receive lines. Now we can see that down here, and I'll mention this now before I forget, down here it went green even though I used a straight through. So that's the same thing as this right here, right? That's because modern devices are capable of figuring out what you're trying to do. So you could connect very strange cabling in many cases between devices and have the devices figure it out. But what we're trying to understand is why we have things like uplink ports, or why we have the ability to use crossovers or straight throughs, or why we want to use them, or why somebody's got a peg somewhere with different kinds of cabling on it. So let's go over some of the differences. Well, first up, there's the very mechanical difference between the two. Now, the standard that governs how we connect, or how we put a connector on a cable, is EIA 568. And there are two different connection types in 568. We've got 568A, and we can see the difference is really in the green and the orange pairs, and 568B. Now, when we have a straight through cable in a data network, one side is connected or terminated the same as the other side. So in the telco world, we might do 568A on one side and 568A on the other side. In the data networking world, the vast majority of cabling that you'll find is terminated 568B on one side and 568B on the other. So pins 1 and 2 will be orange. It's a dead giveaway that you have it. If pins 1 and 2 on both sides are green, then you know you've got 568A on one side and 568A on the other. When we have a crossover, what we're going to do is terminate one side with 568B and one side with 568A. And what that does is it transmits pins 1 and 2 to pins 3 and 6. Ethernet uses pins 1, 2, 3, and 6 for data. And so we have a transmit pair and a receive pair, and when we do a crossover cable, what we're doing is we are sending transmit to receive, so 1 and 2 to 3 and 6, and receive to transmit, so 3 and 6 back to 1 and 2. And the reason for that is that Well, I wouldn't talk into your mouth, right? I would talk into your ear. We listen with our ears, we talk with our mouths. And so when you are talking back to me, you're not talking right into my face. I'm hearing your signal in my ears. Same thing is true with a PC or a network interface card. We have to transmit to the receive lines and receive back to the transmit lines. All right, so this is just another illustration of the problem. If I connected just a straight through between two computers or between two routers or between two switches, what ends up happening is I would be sending the transmit wires to the receiving station's transmit wires. But what I really want is to send transmit to receive and receive to transmit. Okay, so this is just another way of seeing that. And then there are all kinds of different devices that we use on the network today that require some kind of conversion. Now, as I said, today devices are very capable of figuring out a lot of these connections. But if you have a legacy piece of equipment or one that doesn't have the intelligence in it, well, now you know why. Now you know why you have to connect sometimes using a crossover cable. Alright, so this has been a short video on some of the cabling that we have in networks today. Now, there are a lot of other considerations that we have when we're building a network. So we just got done talking about crossover versus straight through, and we know that modern devices can figure that out, but older devices sometimes need to be given the very particular cable that they need. But in addition to understanding now EIA, or Electronic Industries Association 568A and B, we also might want to be aware of the different categories of wire. So the smaller the number, the older or the worse off you are in terms of cabling. Category 5, 5E, 6, 7, these are much higher quality cabling, and so given your choice, you want to put in the best possible copper that you can. And this really goes down to the physical construction of the cable and the quality of the copper. And we can see that we have things like twisted cabling together, the pairs are twisted together, and they're even twisted together at different rates per inch. In addition, we have the structure of the cabling itself. In this middle image, you see that that's stranded cable. So a single connector or a single conductor is actually made up of sort of hair-fine filaments of copper. This is as opposed to solid pieces of copper in each conductor. Now, what this buys you is lots of flexibility. You have the ability to twist your cables and everything else. This is an example of a patch cable. So a patch cable is very, very flexible, right? I can bend it, I can twist it, I can do all kinds of things with it, and it doesn't break. And that's because the cabling inside here, or the conductors inside here, are stranded. Now, the problem with stranded, seems like a really cool thing, but stranded also has much higher attenuation. So the electrical signal quality is worse in stranded than it is in solid core, which is why we use solid core in the walls. By the way, the walls are also always straight through. So that's some of the other differences that we see in cabling, so be mindful of that. That's also why you want the shortest possible patch cable that you can. You don't want 50 feet of patch cable because of that attenuation. That also will restrict your data throughput capability. Well, I think that'll do it. This has been a quick video on crossovers versus straight through cabling, why we use it, why we sometimes need to use a particular kind of cabling, and of course what modern devices really have the capability to do. But also we talked just briefly about solid core versus stranded and some of the other categories of wiring. Like and subscribe if I helped, and may those packets always reach their destinations no matter what kind of cabling you decide to use.